So hello everybody, my name is Laura Foini. I'm a CNRS researcher in Saclay, close to Paris. I'm grateful to the organizer for this invitation. It's great to be here, participate to this conference and come to Bangalore for the first time. I'm going to talk about a work which concerns open quantum system, which is a broad field of research. And I will explain better what our context. Before, let me acknowledge my collaborators. The first is Satya Majumdar, who was a former PhD student with me and Alberto Rosso, who is now in Toulouse. Oscar Dupuy, who just started his PhD, but worked hard with us during his master. Alberto, of course, Rosso, and Thierry Giamarchi. So, as I said, open quantum system is a broad field of research, and there are different types of approach to this type of phenomena to describe the interaction of the system with another environment, let's say. And as we have seen, for instance, in the talk of Camille yesterday, you can, many people focus on the Lindblad approach, when you assume that the dynamics of your density matrix is Markovian, so you forget the memory at every time steps. And this is typically used to describe the high temperature regimes of your system. And instead, what we are going to focus on is another type of approach, which was pioneering by Caldera and Leggett in the 80s. And where you think that, where you model your thermal bath as a collection of harmonic oscillator. This is just for convenience because it's quadratic, so you can integrate it out. And just after specifying some few properties of your bath, you can then have an effective model for your system once that you have traced out the bath. So this type of bath typically have long-range correlations in time, and are typically studied in the low temperature phase of your problem. And on the extreme regime, I put here quench disorder, which is not at all what you call a bath, but it's still an interaction of your system with your environment when you assume that this system is static, basically. So you have quench disorder, which gives rise to a completely different phenomenology of systems that we have just heard a talk about that. And Fabian also gave a very nice talk. So why we ended up studying this problem, because in the literature, there are two types of localization which are discussed. One is the many-body localization that we just saw with quench disorder. So you have in the simplest case, when there are no interaction, you have an Anderson insulator where transport properties are suppressed. But people studied also the case when you introduce interaction and the type of phase diagram that you can encounter. And this is also characterized by suppression of transport properties. And on the other hand, there is a type of localization which is discussed in the context of open quantum system, which occurs for instance, in the spin boson model. So you have one spin coupled to a collection of harmonic oscillator with some particular properties in the spectral function. And what it happens is that under some condition, you can have, if you initialize the spin in some up condition, for instance, and you let it evolve, it fails to thermalize. Basically, it maintains some memory of its initial condition. You can also describe a thermodynamical phase transition at the level of the ground state. And okay, this is another type of phenomenology. And what you wanted to do was to study a many-body version of this spin boson model, where in our interpretation, so the bath was sort of acting as an yield disorder. And even if the physics of an yield disorder is very different from the one of quench disorder, we wanted to try to make some connection between all these different problems and try to see if there is some reason to talk about localization in this many-body context. So the problem that we focus about, so the spin, the system Hamiltonian is the one of a spin chain. We have a spin 1/2 chain with, well, it's the XXZ chain. You have interaction between X and Y, and then a term which couples the ZZ interaction. Now this model, as we have seen, is equivalent to a model of interacting fermions, and the Z coupling corresponds to the interaction between the fermions. And what you can do is so this model conserves the magnetization or the density of the spins of the fermions. And what you can do is to study either the problem metal filling, so mainly that the density is 1/2 and the magnetization of the chain is 0. And I will call this case the commensurate case because the density is commensurate with the lattice. Or you can study the problem in the dope case where the density is something between 1/2 and 1. And I will call this case incommensurate. And this is what the main focus of my talk. To treat this problem, we will apply, and then the interaction also with the graph, we will apply bosonization techniques, which is a technique which allows to, so maybe I didn't stress before, but what we are going to do is to describe the problem at 0 temperature. So we're not at high temperature. And this bosonization formalism is well suited to describe the low energy excitation of your problem. It's convenient because basically you ended up studying, instead of this complicated interacting Hamiltonian, a quadratic action. This is the action in imaginary time, so when you want to study thermodynamical properties. And so the mapping, so I'm not going to review the mapping, but just let me say that you have this quadratic action of a field phi, which enters in the definition of the sigma z operator, so the density of the spin. And two important parameters of the problem are the speed of sound, because it has the excitation, has a linear spectrum, this problem, with a speed of sound u, and the Latinger parameter k. K is an adimensional parameter, and it controls the decay of the correlation of, it is the exponent which controls the decay of correlation in your system. Indeed, without the buff, the problem that we are studying is a critical phase with power law correlations. And other important properties that it has a finite compressibility or susceptibility in terms of the spin chain and a finite spin stiffness. And from the purposes of transport, it is a perfectly conducting phase with a Drude peak. Sorry. Now it comes how we put the interaction with the external environment. So what we suppose is that we have our spin chain, and in every point we put above la caldera legget, so this set of harmonic oscillators. And what is important is, one, that these baths are independent on each side, and the other part, which is crucial in this type of model, is to what it is coupling. Of course, it determines the physics of the problem. And the coupling that we do is via the density of the fermions, or the magnetization of the spin chain. So we suppose that the spin buff interaction is a coupling between Z and all this, the X position of the oscillator in this way. What we can see is that this is an operator that to enhance the fact that it's an operator and it has its own dynamics, I write it as h of t. I could say that it depends on time, even if, I mean, it's an equilibrium. I'm studying equilibrium property, so it is time dependent. The time dependence here is put just to emphasize that it is an operator. And this has to be contrasted with the case that I was talking about in the introduction, when this operator is actually a random number, which is completely static, and it turns out to be the model which is studied in the many-body localization physics. So I have to tell you what are the properties of the field, as the buff is quadratic, as already mentioned. You can integrate it out, and everything will depend just on the two-point function of the buff. And the dynamics of the buff is encoded in the spectral function, which describe the low energy excitation of the buff. And it is customary to take, there are type of paradigmatic representation of this spectral function, which consists in considering this as alpha is just the strength of the coupling, and omega to the power s is the dependence on omega. And the exponent s describe the properties of this spectral function. And it is usually distinguished because it gives rise to different type of physics between the ohmic case where s is equal to 1, the subohmic case where s is smaller than 1, and the superohmic case where s is bigger than 1. Okay, so in the end, once that we have integrated out the buffs, the type of function that we deal with is a long-range so at this point we have a two-dimensional classical. We are in imaginary time, and we have a two-dimensional classical field theory with long-range interaction. It is anisotropic because the long-range interaction are only along the imaginary time, and we have this type of due to the representation of the density in terms of the field phi, we have this type of cosine term here in the interaction. And this kernel here, tau minus psi prime 1 plus s, is due to the type of dissipation that we have chosen. And so the exponent s here is the one that I was talking about before. So this is a non-integrable problem, and in order to solve it, or at least to understand its property, we have applied Gaussian variational method, which is a method that consists basically in assuming taking as a variational ansatz an action which is quadratic in phi, and then optimizing over the propagator, and that's it. And then see, depending on the property of the propagator, the type of physics that you have. The perturbative renormalization group and the numerical simulation. Numerical simulation have been done using Langevin dynamics, basically because once that you have this two-dimensional field or interface, you want to sample equilibrium configuration of this action. Now the Langevin dynamics is performed with a classical temperature, which is equal to 1, which should not be confused with the quantum temperature, which describes, I didn't put it here, but it's the length along the imaginary time direction. So some important quantities that characterize the system are the compressibility, which basically describes the small q behavior, the spin stiffness, which describes the small omega behavior. And if one is able to have an analytical expression for the propagator, one can perform analytical continuation in order to have the transport properties and the conductivity. So this problem, so these are the results of the RG computation. I should acknowledge that Miguel Casalilla and his collaborators studied this problem before us in some context. And they derived the RG for this problem. And so you have a flow for the Lattinger parameter and the interaction with the buff. And it is a type of Sine-Gordon XY flow, which describe this type of phase diagram where you have a Lattinger liquid phase here, where when alpha is irrelevant, which separates from a strong capping phase that we have to characterize. And the critical value of the Lattinger parameter at the transition depends on the exponent of the buff. And the type of transition is a BKT type of transition. So the RG is not telling us to what happens in the strong coupling phase. And so we perform this Gaussian variational method, which predicts that you have a Latinger liquid phase with the propagator that you imagine. So for what happens in this phase is just the buffer normalize the parameters of the Latinger liquid action. And you have, instead, if you are at stronger coupling, what happens is that you enter a dissipative phase where the omega square dependence that you had in the Latinger liquid phase is replaced by a fractional omega to the power s term proportional to eta, which is just the strength of this term. And okay, so there is an order parameter which characterizes this phase transition, and I will tell you what is. I will tell you later when what it represents. Is the cosine of 2 phi, and one can using the variational ansatz that I showed you before. One can conclude that if you are in the Latinger liquid phase, this order parameter vanishes with system size in a power law manner, which depends on the renormalized Latinger parameter. And instead, in the dissipative phase, it converges to a constant where with some correction. And these are the results that we did with this numerical simulation of Langevin dynamics, where you see that you will find for smaller alpha, we find compatible results with this prediction. And for stronger alpha, we see that this order parameter converges towards a constant. Now, the other properties that I was saying is the compressibility. And what happens is that the compressibility in the Latinger liquid Hamiltonian is expressed by the ratio of U over K. What happens with the buff is that U is renormalized and K is renormalized, but the ratio U over K is not touched. And this is because there is a symmetry which concerns a part of the action which interacts with which describes the interaction of the buff, which is the fact that if you have your field phi and you apply a tilt along the x direction, this is the dissipative part is independent of this. And this tilt is what you would like to introduce with the bosonization when you want to change the density of the system. And due to this symmetry, let's say, it's called in physics statistical symmetry. And due to this property, what happens is that the compressibility is untouched. So that in these diagrams here, you see the same parameter that I was showing before. And now you see that in the Latinger liquid phase, if you look at small q behavior of the propagator, you see that is equal to 1, which is our bare value, let's say. And it is exactly the same, so it is untouched in the Latinger liquid phase, but also in the dissipative phase is equal to 1. Now, in order to understand the small omega dependence, we have considered this quantity. And in the Latinger liquid phase, you expect that it diverges for a small omega as omega to the -1 or omega to the minus s over 2 in the dissipative phase. And this is what you have seen numerically in this plot. We have multiplied this quantity by omega to the power 1/4 because I forgot to say, sorry, that these simulations are done for subomic buff with s equal to 0.5. And here again, you see that at small omega, it converts towards a constant. And so the net result of this discussion is that what happens is that this dissipative phase is a spin density wave. So the value of the order parameter I was discussing before is the amplitude of this spin density wave. The period is the Fermi momentum, which is related to the density of the system. And but the particular properties of this spin density wave is that it occurs in absence of opening of a gap. So it is a gapless phase, which is induced by this fractional term omega to the power to the s. So as we have a variational ansatz for the propagator, we can try to do the analytical continuation. And what happens is that if you compute the transport properties linear response and you compute the DC conductivity, you get that for ohmic system it is a constant, but the peculiar property is that for subohmic bath, this extrapolation to real frequency predicts that the conductivity is 0. And this is coming back to the introduction of my problem, explain why motivate how to call this phenomenon as a localization induced by the bath. I don't have much time, but okay, I think I can get it. So what happens if you are commensurate is that you still have a BKT transition, but towards a spin density wave, which is commensurate, and where, of course, with a gap. So it is a different phase of matter with respect to what I had before. And this is the phase diagram. So it's an antiferromagnet. And in the spin chain, also in absence of the buff, you have this antiferromagnetic phase. And then, but the result of the buff is that it enhances this order. It occurs, this is the phase diagram as a function of the Latinger parameter at the exponent of the buff. In absence of the buff, it occurs at the value of the Latinger parameter equal to 1/2, but with the buff, it occurs, you have this enhancement, let's say. And so I didn't, during my talk, I didn't cite, I wanted just to flash some paper, I'm sorry, probably there are many more, so that pointed out this phenomenon that study system with on-site dissipation and show this phenomenon that you can have this order induced by the bath. But of course, the type of phase of matter depends on the type of coupling that you have with the bath. For instance, in this problem here, they were coupling to the bosonic operator and have a different type of system. And instead coming back to the interaction and go a bit to the perspective, what I would like to do, it would be, if it is possible, maybe to do some more connection with the problems that are around in the literature. So with Markovian evolution or with quench disorder, if it is possible. For the moment, we're still working about that. And this brings me to the conclusion. So I wanted to tell you that you can have order induced or enhanced by the bath. And in some particular case, you have the emergence of this phase, which is a gapless spin density wave. What we are doing now is to combine the results of the commensurate and the incommensurate results, because what happens, we have these three phases, the Latinger liquid, the antiferromagnetic phase, and this gapless phase. And what happens if you study the full phase diagram as a function of the magnetic field, you expect to have a phase transition between these three phases. And what we are studying is basically the commensurate-incommensurate phase transition, which should occur between the gapless and the gapped spin density wave. And we have some computation going on considering the entanglement between the system of the bath. And as I said again, maybe we'll be able to draw some more connection with open quantum system. And with this, I conclude, and I thank you very much for your attention.
Questions? I had one question.
Yes.
You studied this commensurate phase.
Yes.
But suppose QF is 1/3.
Yeah.
Would everything go through or would it be different?
Yeah, I think that should put some longer range, some other type of interaction which are able to stabilize 1/3.
Is there a phase locking or, you know? period locking, which is...
Yeah, with this type of interaction, I think that the phase 1/3 is not, in the commensurate case, is not, you have just a...
it's a point, it's not an extended region.
Yeah.
Okay. Yeah, please.
Yeah, so what would like is not, I think that what my interpretation is that is an anneal disorder. So the physics is different. You don't have many metastable states of this type of physics. But the analogy that we would like to do is with the Bose-Glass. And when I'm talking about this phase diagram as a function of the magnetic field, I have in mind this phase diagram with the lobes and the phase diagram in between the Lattinger liquid and the superfluid and the Bose-Glass phase.
So you study spins, right? And each spin is coupled to a different bath.
Yeah.
Would you maybe comment what would be the picture if there is a common bath for all the spins?
Yeah, so we didn't study this, in my view. So you might have some competition, because if you have correlation between the bath, like here is for free that the bath allows you to do an antiferromagnet, let's say, and in my point of view, but I don't know, because we integrate the bath, so we don't see what the bath does. But in my point of view, the fact that you are able to arrange your system as you want and to do this spin density wave is right, because the spatial correlation of the bath are negligible. Instead, if your bath would like to be the same on larger time scale, this could be compete with the order that you want to establish. But we didn't study this, so it's something to.
Okay.
Tell you which one is the most relevant, I mean, concerning the type of coupling to the bath. I mean, either having an individual bath for each spin, or whether having the same bath for all of them.
Yeah, so I don't really have an experimental. Physically, probably something, well, there is something in between with some correlational length, but yes, I don't have an experiment.
Okay, so let us thank the speaker.
Thank you.
And go to the next talk by